Right now, two identical machines are tearing through the dark at 60,000 kilometers per hour, over 25 billion kilometers from Earth. Voyager 1 and 2 are the most distant human-made objects in existence, currently navigating the vast, empty interstellar medium. To understand how they got there, we have to look back to their launch in 1977. At the time, spaceflight relied entirely on chemical rockets, which presented a massive physical limitation. Spacecraft lacked the delta V, the total fuel capacity and thrust required to fly a direct path to the outer planets. Reaching the gas giants was hard enough. Accelerating sufficiently to achieve solar escape velocity, permanently leaving the sun's gravitational pull, was mathematically impossible using only the propellant a rocket could carry. The solution came from NASA engineer Gary Flandreau in 1965, during an analysis of planetary orbits. Flandreau discovered that the solar system was approaching a rare geometric alignment of its four largest outer planets. This alignment offered a way to bypass the limits of chemical rockets. By executing a series of flybys, a spacecraft could use a gravity assist to harvest kinetic energy directly from the planets themselves. Voyager succeeded through the calculated application of orbital mechanics, harvesting the kinetic energy of the planets to overcome the limits of rocket fuel. This map shows the orbits of Jupiter, Saturn, Uranus, and Neptune. Flandreau proved that in the late 1970s, these four planets would slowly converge into a one-sided geometric arc. This exact planetary arrangement happens exactly once every 175 years. This physical alignment translated directly into a highly specific mission architecture. It created a temporary launch window where a single probe could swing past Jupiter, use its momentum to reach Saturn, and continue chaining encounters all the way past Uranus and Neptune. The physics of the solar system delivered a strict ultimatum: launch by 1977 or wait nearly 2 centuries for the next opportunity to explore the deep solar system. The process powering this maneuver is often called a slingshot, but that implies tension and snapping back. In the planet's frame, Panel A, the spacecraft enters and exits at the exact same speed. But shifting to the Sun's frame in Panel B, we add the planet's forward orbital velocity to the exit trajectory. The spacecraft experiences a massive net gain in speed. The spacecraft physically steals a microscopic fraction of the planet's orbital angular momentum. As a result of this physical exchange, the enormous mass of the planet slows down by a fraction of a millimeter per billion years, while the lightweight spacecraft accelerates by tens of thousands of kilometers per hour. Instead of carrying heavy fuel tanks, the mission used the planets themselves as kinetic refueling stations. This solved the delta V deficit entirely, without burning a single drop of onboard propellant to gain that speed. Voyager 2 launched in August 1977, setting its initial trajectory straight for Jupiter. It arrived in 1979. Among the data returned were the first ever confirmed observations of Jupiter's faint ring system. As it passed Jupiter's moons, the probe photographed the pockmarked surface of Io. This provided the first definitive evidence of active extraterrestrial volcanism. Using Jupiter's orbital momentum, Voyager 2 bent its trajectory toward Saturn, capturing the gas giant and its ring system. The assist from Saturn propelled it outward again, reaching the blue sphere of Uranus in 1986. Finally, a third gravity assist sent it to Neptune in 1989, documenting its deep blue atmosphere and the storm known as the Great Dark Spot. Voyager 1 launched 16 days after its twin, but it was placed on a faster, divergent mission path. Its trajectory was designed to prioritize a close flyby of Titan, Saturn's largest moon. NASA targeted Titan because ground-based observations suggested its thick, orange atmosphere harbored complex chemistry and the potential for liquid on its surface. Prioritizing this moon was a deliberate sacrifice. The geometry required for the Titan flyby flew Voyager 1 up and out of the solar plane. This ended its planetary tour early, but it granted the probe a direct, high-speed path out of the solar system. This schematic shows the heliosphere, the plasma bubble generated by the solar wind. The heliopause marks the exact boundary where the solar wind collides against interstellar space. Voyager 1 traveled for 32 years to reach this extreme edge. On August 25, 2012, telemetry data indicated that Voyager 1 had officially crossed the threshold. Because no probe had ever recorded the plasma density of interstellar space, it took NASA scientists 8 months of analysis to definitively confirm the data. Passing the heliopause proved that human engineering could operate beyond the protective bubble of our local star. It transitioned our physical reach from a planetary scale to a truly interstellar one. In February 1990, Voyager 1 was roughly 6 billion kilometers from Earth. At this distance, NASA scientist Carl Sagan requested that mission leadership instruct the probe to turn its cameras back for one final sequence. The resulting image captured the Earth as a single, sub-pixel dot suspended in the dark void of space. To preserve power for the interstellar crossing, NASA commanded the cameras to shut down, forever. This final engineering necessity captured the entire human world as a sub-pixel dot, isolated in the void. Attached to both spacecraft is a long-term passive payload, the Golden Record. It is a gold-plated copper disk designed as an analog data storage device. Encoded within the grooves is a dense layer of scientific information, including 115 images, diagrams of the structure of DNA, and the mathematical parameters of our solar system. Alongside the science is a cultural data layer, preserving spoken greetings in 55 languages and human music, including an Indian raga by Shorshri Kesarbai Kirker. Today, the radioactive isotopes powering the Voyager probes are steadily decaying. In the near future, their signal transmissions will permanently cease. Because the gravity assists granted them permanent solar escape velocity, the dead hardware, and the golden record it carries, will continue drifting through the galaxy. They will act as a cosmic fossil, silently preserving the evidence of human existence long after the Earth itself is gone.